Okay, so this is a problem where you had a red laser pointer, you shot it at a mirror at 45 degrees, it bounces off the mirror, and the question is, what is the force on the mirror from the light? This is a problem that IB could throw onto your exam. So they're not gonna tell you the wavelength of the light. They're just gonna say it's red. So you have to know that it's close to 700 nanometers, right? And so we've done this, if you're watching the video, and we parsed it into steps. And so we said, okay, after some thought, by the way, you will have no time to do any of this on the exam. But we have time now, so this is good to parse through this and take our time with it now, so that on the exam, hopefully you have a chance. So we said, first we're going to find the wavelength of the light, 700 nanometers. And then we're going to find the energy of one photon. So the energy of a photon is hf, and f is c over lambda. That comes from the universal wave equation. So hc over lambda. So let's work through the numbers over here. I'm going to erase this now. Yeah.
Your phone is falling.
It's falling?
No. Or it's like
oh, it needs to follow me over here. So thank you. The video watchers, thank you. Okay. So the first thing we need to do is we need to say the energy of one photon is hc over lambda, right? So this is 6.63 times 10 to the negative 4, that's Planck's constant, times 2.99 times 10 to the 8, that's speed of light over our wavelength, which is 5 times 10 to the negative 7 meters. Oh, dude, I keep doing 5. Why do I keep thinking red light is 5? It's not.
It's 5 million.
I'm getting mixed up with the milliwatts. So if this were me, that's close, that's like 0.9 times 3 is like 2.7. So I would do this like 2.7 times 10 to the, that's going to be negative 26 plus 7 is negative 19, is it? Or so, and this is going to be in joules, okay? You can do this with your calculator. I'm just too lazy. Okay, so this is the energy of one photon we have now in joules, right? It's not very big, but there's a lot of photons, so it does make a difference. And then we say, okay, we're hitting at 45 degrees. So we deal with that and we say, at a 45 degree angle, bless you, our vector coming in, the part of the momentum that is perpendicular, there's normal to the mirror, is 1 over root 2, and then we're doubling it because it's hitting and coming back. Right? So that part of the momentum is bouncing straight back out, so you have to double it. And as Grosch says, this is really just equal to root 2. Okay. So we get that. And then the next part, we have to get the change in momentum from the energy of one photon. And so our change in momentum, our momentum of one photon is E over C. And so, bless you. And so you do kind of recognize, we could have just gotten rid of this C, right? And we could have just said that the P is H over lambda. But if we take that and divide by this, it's going to be, what is it going to be? We're going to get rid of 8 of those, so we're going to have negative 27 again. So about 9, sort of like, yeah, somewhere around 0.9 times 10 to the negative 27. And we would say this is kilogram meters per second So somewhere around there. I don't know.
Exactly.
Exactly?
Yeah, Newton cycles.
Yeah, that's just a unit of momentum. But again, momentum is weird with photons. They work in the like mass formula to derive things for a photon which has no mass, but we go with it. Okay, so this is my change in momentum of one photon, right? So this is per photon. And that is going to be multiplied by my 45-degree thing, which is really just times root 2, which is 1.4. So we'd say our total, this is just the momentum of the photon, not the change in momentum. This is the momentum that the photon has coming in. And the change in momentum is going to be 2 over root 2 or times root 2 of that. So if we times this by 1.4, we're going to have maybe like 1.3 times.
10 to the 16. Oh, wait. Yeah.
It doesn't gain the momentum, it changes that much momentum.
Just the direction that changes?
It's the direction and the magnitude. So like if you take a tennis ball and you throw it against a wall, or you bounce it on the ground, right? The time between when it hits the table and when it comes back, if whatever the momentum of the ball is going into the table is coming back out at the end, right? If it's an ideal situation. And so your change in momentum is double the momentum that you had going in.
Oh, that means the negative.
Because it's minus the negative.
Oh, so this change in momentum is bigger, which means it does ricochet.
Exactly.
Okay.
Yes, it does ricochet. And that's why you have to put force into when you hit a tennis ball with a tennis racket or something, right? By the way, this is a bit of a weird aside, but how is this possible? Like we're just like taking a component of the momentum vector and we're just doubling it. Like, isn't momentum supposed to be conserved?
Well,
Well,
it's vectors.
it's vectors. Yeah, it's vectors, but like...
One is pushing back, but the thing doesn't have a mass, so it's going back.
Okay, golf clap for Carter and for Karosh. If the mirror is here, like when Karosh shot the laser, shoot the laser pointer on here. Thank you. When it's hitting here, that light is actually reflecting, right?
Yeah.
It's not a great mirror, but if it was, it would be reflecting back. You wouldn't see it if it wasn't reflecting, right? Which is why a really good laser, you can't see it, right? What's happening to the board right now? It's getting pushed back, but I can't see it get pushed. If you were in space, if we were all floating in space, I really want to do this field trip one year. And this board was floating in space, and we were all perfectly still, and Karosh shot the laser pointer and hit this. What would happen? The board would move, and Karosh would move as well. And we'd be like, bye-bye, Karosh. And slowly over years, he would get further and further from us. The board would get further and further from us and everything. And so the momentum is conserved, okay? I want you to know that. The mirror is pushed back as well. So we're not just doubling it out of nowhere. Okay, so this is the change in momentum per photon, right? Don't shine that in my eyes.
I'll try not.
It's only 1 milliwatt, probably fine. This is a really weird aside, and I'm making a video, so I'm going to say it really. There was an NFL game played in Mexico City, just once, and Tom Brady was there, and he was playing, and you should have seen the stadium. Like, actually, I love Mexico, okay, I want you to know that, but this stadium is like, doesn't have very many games in it, but it's a massive old stadium, and so they put an NFL game in there, and for whatever reason, people got in there with laser pointers. And so there was like, the whole game, Tom Brady had like lights on his helmet like the whole time. And they had to be pretty, like to shine that distance, you gotta have a pretty strong laser pointer. But he didn't go blind, so that's good. Okay, that was all I had to say. Okay, so what do we do next? We've done number 4, right?
Multiply by 1 second.
Good, so now we need the force from the change in momentum. And this is an important little doodad here. So force equals mass times acceleration, which equals mass times delta V over t. And so F times t equals m delta V, and m delta V is my change in momentum. I know this is for something with mass and we're dealing with photons, but we just go. The time for us is 1 second. Why? Because it's a watt, which is 1 joule per second. So if we're using that amount of joules, our time has to be 1 second, which means our force is the same as our change in momentum. So this is also equal to the force per photon. Okay, and so now we need our number of photons. How are we going to do that?
Divided by 5, divide the, what's 5 megawatts energy of 1 photon by the 5 milliwatts of the.
Good, so we're going to do our total energy divided by the energy per photon. We did find that energy, didn't we?
Isn't it 2.7?
It's that one, right? See, we did do this for a reason.
Yeah.
So our total energy is 5. This one is a 5, right?
Yeah.
Times 10 to the negative 3.
Well, that's their power.
Yeah, but this is the joules per second. And we're going to divide that by our 2.7 times 10 to the negative 19. So this is the joules per photon. This is my total energy in my beam. So now I can find out the number of photons, which is going to be somewhere around 2, maybe 1.9. No,
Can you have like half a photon?
it's a little bit more than, no, it's a little less than 2. Yeah, like 1.9 or so.
Can you round a photon?
Well, hold on, because there's a lot. So negative 3 minus 19 is like 16, right? So 1.9 or so times 10 to the 16 photons.
Negative 3 minus 19? O plus O.
Yeah, negative 3 minus negative 19. So that's my number of photons, and if I multiply that by the number of newtons, so this is newtons per photon that we calculated before, right? This is the newtons of force per photon. Dinger, talk to me.
Not photons per second. That's already.
Yes, photons per second. That's right. And we're doing everything per second because we were given watts. Right? So that's an interesting, that's a unique thing.
So would there be about 1.2?
So we got the momentum per second, we got the energy per second, and we're doing everything per second. That is correct. Yeah.
So would there be about 1.2 times 10 to the negative 11 newtons of force?
So we do this number of photons, and then we multiply that by, multiply these two together, right? So 1.3 times 1.9 is like 2.5 or so. Didn't you get 2.4? Nathan? And then negative 27 and 16 is negative 11? Is that right?
Yeah.
So I'm just taking this number, the newtons per photon, and I'm multiplying it by the number of photons, and this is my newtons. Okay, so that's the force being exerted on the mirror. It's not very much. Is there, do you think there's any time ever where you're going to actually be able to measure in the real world the force of a photon, like of lights? Yeah. Where would you be able to measure it? In space. Yeah, so what's the fastest thing humans have ever created? No.
A particle accelerator.
No. Well, yeah, okay, so, yeah, fine. But not the, but we didn't build the particles.
Wait, we made the manhole? Was it that manhole?
The manhole was the fastest for a long time. Yeah, for a long time, the manhole. There was a manhole in the Trinity test when they first tested the atomic bomb, and they didn't realize that the blast would come through the sewer corridors, and a manhole cover. And it was just in one frame of a picture. You saw this manhole, and the next frame it was gone. And then they calculated the speed, and that was the fastest thing people had ever created. And then after that came
Who was Hamilton?
What? Drive to Survive. I like it too. It's good.
It's so good.
The spacecraft Voyager is still the second fastest thing that humans have ever created. It's traveling out there right now very, very fast. But the fastest thing we've ever built is the Parker Solar Probe. It is right now orbiting the sun. Pretty close. It has an amazing heat shield that keeps it from getting vaporized. But on the way in, it was accelerated by the sun's gravity, right? But it got slowed down, actually like perceptibly slowed down. Why? Because when you get close to the sun, like you feel sunlight, right? But think about those sunlight rays that have come from the sun. What are they doing as they get closer to us? It's a sphere, right? They get farther and farther and farther apart. So by the time we get the sun's photons, we'll talk more about this, they're quite spread out. When you get close to the sun, those photons are concentrated, and it actually breaks the Parker Solar Probe on the way in. You can actually feel it. I'm gonna stop this video now.
So can we then get Pirates of the Caribbean in space?